So hello everyone. As said before, I'm the only thing between you and lunch, so I'm trying to make this as entertaining as possible. My name is Robert Kubis. I'm a developer advocate for the Google Cloud Platform. So now what does that mean? Like I usually try to explain that because not everybody knows what that job basically entails. We understand ourselves as the bidirectional interface between you who built on our platform and the developers inside of Google who built the platform. So please, 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 please reach out to me or any of my colleagues with anything in terms of like feedback, things where you think they don't work like as they should or supposed to be to work, or where we can actually improve. We need your feedback to improve the products. Now, I'm going to start a little bit with a background around Spanner. Google Cloud Spanner, and then go into some like use cases, where it is used, how it compares to other databases. I'm going to explain in a little bit more detail how Spanner works. And at the end, I'm going to show a little demo, like how to actually interact with Cloud Spanner and how to get started. All right, so let's start with the background. Let's look at 2005, roughly, like 12 years back. Google at that point was, like their main business, AdWords, was on the back of a MySQL, a sharded MySQL system. And that MySQL system was sharded by customer ID. And we were growing rapidly. We were growing from a like 10 million per year business to like $1 billion a year business in like a couple of months. So we needed something that is flexible. We needed something that can scale with our business. And MySQL, we basically had to reshard MySQL multiple times to accommodate the growth. Now, in the last reshard that we did on our MySQL system, on our sharded MySQL system, took actually several years. And that was nothing that was viable for us going forward. So what did we really need? We needed a database that is horizontally scalable. Right? So we needed a database where we can add resources and it scales quasi-linear. We needed this database system which still provides things like traditional relational database systems like asset transactions and global consistency. We were dealing with money. We were dealing with partners, agencies, so we couldn't accept any eventual consistency. Another thing which is really important was that we couldn't accept any downtime. Google is a 24/7 business. And anytime we are down, basically, we are not only losing money ourselves, more importantly, we're losing money from our customers. Right? They cannot run any like advertising and things like that, so we needed a system which is 24/7 online. So we needed a system where we can do things like hardware upgrades, security patches, schema updates, while the system was running. So that's how Cloud Spanner was built inside of Google to replace a sharded MySQL system. It was built from scratch, but it was still with the semantics and the ideas of a relational database system. We didn't want to retrain all our developers. We wanted to tap into their knowledge. We wanted to give them something familiar that they can work with. So what is Cloud Spanner? Cloud Spanner is basically our internal Spanner system, which we brought into the world of cloud. So into the world of cloud, it means we had to integrate it with a lot of our tools inside of Google Cloud Platform. So we integrated with our developer console, we integrated it with identity and access management, but also what was really important is we integrated in the sense that you basically can go into the developer console and say like, okay, I want to have an instance, 3 nodes, you click OK, and you have your instance in a couple of seconds. So it's a fully managed database service which is at global scale. What's also important, it's not only a regional service. Spanner actually is capable of doing global replication, and that's synchronously. And what's also really important is if you tap into Spanner, if you want to try it out, if you use it, you can be sure this is a battle-tested system. This is a system that we actually back many of our systems on. So for instance, Gmail, the Play Store, many other products are on the back of Spanner. Another thing that we needed to accomplish when we were making it available as a product was that we wanted to tap into open standards. So we spent quite some time to implement things like client libraries, first and foremost Java client library, but also other languages that we support like Python, Go, Node.js, and many, many more coming up. We also have a GDBC driver, but there's a caveat to the GDBC driver. It's currently a read-only GDBC driver. That might sound weird at the first sight, but the thing is, like a lot of BI tools don't need the right capabilities. So even though this is a read-only capable GDBC driver, it still enables you to integrate with a lot of the BI tools that are out there. All right, so how does Cloud Spanner actually compare to other databases? Now, I want to compare that with two ends of the spectrum. On the one hand, we have the traditional relational database system. On the other hand, we have like the NoSQL system, like document or JSON-based database systems. Now, when we compare a Cloud Spanner, like oftentimes we get compared against a single instance MySQL or Postgres. And I want to like ask really quick into the room, who has run a MySQL or a Postgres system here in the room? Okay, like the majority. Who has run a sharded MySQL or Postgres system? Okay, there's a couple. I feel with you, I'm sorry for you, but it's a pain. It can be really a pain unless you really know what you're doing. It is basically something that is, yeah, fragile. It can be very fragile. Now, we get most of the times compared to a single node system. But even if we compared ourselves to a sharded MySQL or Postgres, there are a couple of things that there are to mention. Now, first of all, if you compare us against a single node or a sharded MySQL, usually, like, let's imagine you have a setup of you have a master, you have a failover instance, and you have some read replicas. So now, why do you have read replicas? Most of the time, where you like basically your scalability boundaries is with a sharded system is the write throughput that you can achieve in your sharded system. Now, to free up your master from some of the read workload, to free it up for more writes, you basically have read replicas, and you offload some of the reads to the read replicas and free up your master for some more writes. Now, in the scenario where you want to do a hardware upgrade, what do you have to do? You basically have to fail over to your failover instance, which even though it's a planned downtime, it is an incurrent downtime which you will have. Even if it's only short, there will be some downtime. Then you take down your master, you do upgrades, there's some operational risks if you bring it back online that something happens, so it's not very easy, right? The next thing is, as mentioned, scalability. So you can only hope, like, if you run that on a cloud provider, that cloud provider provides a bigger machine. Because a traditional relational database system, you basically can only scale upwards. You can scale vertically, but not really horizontally. And then the other thing is like all the configuration management. It's a hassle and, as mentioned, complicated. Now, on the other hand, if you compare us to a NoSQL database system, there are a bunch out there. You probably all know them. Like anyone who uses Cassandra or Mongo? Yeah, a couple. All right, so with Cassandra, you have something that is basically tweakable consistency, but by default, like these systems are eventually consistent. So they are systems which are not like strong consistent, where you don't have like the asset transaction semantics of a relational database system, right? You, most of the time, unless you install some third-party, some extensions, you don't have an SQL interface. So there's like a proprietary or some other ways of interacting with NoSQL database systems. And of course, they are like designed to be scalable, so they're horizontal scalable. Usually also they're like easier to set up in a high available mode, but it's a manual task to do. So what are typical use cases for Cloud Spanner? And I don't want to go into detail of all of these, but I want to like mention a couple of things for Cloud Spanner. On the one hand, if you have a system where you run out of write and read throughput capacity, that's where Spanner comes in. So if you have like a transactional system, like financial system, for instance, where you need a lot of writes and reads, that's something where Spanner can come in. Spanner can scale horizontally on reads and writes. Another thing which is important if you look at traditional systems, relational database systems, for a single host, your boundary is usually in a couple terabytes of data. So if you have a lot of data, that is another thing where Spanner comes in. If you want to scale on the data size, you can also use Spanner on that. But again, Spanner is not only for large amounts of data. If you need high write and read, you can use Spanner, but also, which is really important and is one of the prime qualities of Spanner, is if you need a mission-critical system. If you need a system that is online 24/7, which is available 4 nines for our regional, which is like 4 minutes and 26 seconds of downtime a month, and 5 nines for our multi-regional version, which is like 28 or 26 seconds of downtime a month. This is also a use case where Spanner comes in, because we can do things like security upgrades, hardware upgrades, online while your system is running. So how do we do this? Now we come basically to the architectural, to the more interesting part, hopefully, of this talk. Now, before I go into the nitty-gritties of like how Spanner works under the hood, I want to like put a baseline out there on the terminology. So first, we start with an instance. An instance is basically our resource pool. So you define in an instance how many nodes you have, and with how many nodes you have, you basically have your storage scalability. So each node supports 2 terabytes of data. So if you have 3 nodes, you can store 6 terabytes of data, and so on and so on. Now, in this instance, you can have a bunch of databases. We support currently up to 100 databases per instance. And then in each of these databases, you can have tables. So that's something, this terminology is well known in relational database systems. Now we have another one, an internal concept, which actually allows us to scale horizontal. And we call that split. What is a split? Split, you basically can imagine if you have a table and you have a primary key, and you have this table sorted by primary key, we basically chop up that table in chunks. And each of these chunks is called a split. And we chop it up basically lexicographically or alphanumerically by the primary key. And then you have basically multiple splits of your table. And that allows us to actually scale. Now, how does it, like, on the hardware side, an instance look like? This is a kind of like a graphic for a regional instance. Now, this regional instance has 3 nodes. And as you can see, so you would buy or lease from us like 3 nodes, but you get actually 9. Because it is replicated in over 3 zones. So in a regional instance, you have 3 zones which are participating to serve your database. And you have the compute separated from the storage, which allows you very flexibly to scale on the compute side, in and out. So now, I mentioned that Cloud Spanner is globally consistent and supports asset transactions. And in a distributed system, this is actually it's a hard problem. So there are a couple of ways to achieve that, to achieve global consistency and make sure basically your data is, in our case, serializability. We have the consistency model of serializability, which is the highest out there. Now, what can you do? On the one hand, you can do a lot of communication. So I imagine, like many of you know, like 2PC or 3PC protocols to do commits. Now you can do a lot of communication, but communication is expensive. And the communication would slow down your system. So we were looking for something else which supports us to do actually this global consistency with reducing the communication. And one way to do this is actually use timestamps. Now with timestamp, there is a problem. If you go and compare your watches right now with the person next to you, and you go off, you wander off, and you meet again in a week, and you compare your watches again, your watches will have drifted, which we call the clock drift problem. Now, why do they drift? There are many, many reasons for drift. There are the reasons like temperature differences, where you have been. There's cosmic rays, there are many, many problems or many, many things that make your clock move forward at different speeds. Now, especially if you have distributed systems where you want to rely on a timestamp, how do you actually make sure that you have somehow globally a wall clock time that you can trust? And for that, we actually built a system that makes that sure, which we called Throughtime. And I'm going to explain what Throughtime is in a minute. But first, what are we using Throughtime for? Now, the thing is, our computer sources are responsible for splits. Each split has exactly one compute node responsible for it. Now, as you see, like the data is replicated across the 3 zones. And we need something to make sure that for these 3 replicas, there's exactly one owner. What do we mean with an owner? There needs to be somebody who's responsible for the group of these splits, so of these replicas, to make sure that they are always consistent in the thing, that they always show the same data. Not like one can update here and another updates something else on the same split. That's not something that we want for global consistency. So we have these 3 compute nodes which are responsible for split 1. And now we have to select somebody in this group which is our leader for this group. And we use an algorithm or like a set of protocols which is called Paxos. So in Paxos, we basically use consensus to choose a leader in that group. So it's consensus algorithm on protocols basically to choose a leader among unreliable participants. And unreliable participants in the sense of you can have network issues or the participants go away, things like that, right? Now we use Throughtime for these Paxos algorithms to make sure that we have at most and always only one leader in this Paxos group. And with this, we can actually make sure that we have global consistency. So what is Throughtime? So how do we make sure that we have a global wall clock time that we can trust? Now, as mentioned, clocks drift. And there is no single point of truth if you just have a timestamp. You cannot make sure that if you have one timestamp, that it's the same all over the world. We somehow need to quantify the uncertainty that I was talking about. The uncertainty of that drift that is happening. And that's what Throughtime does. So Throughtime doesn't give you a single timestamp. Throughtime gives you an interval. It gives you a lower bound and an upper bound. Now the lower bound tells you a timestamp which has passed all over the world. And the upper bound tells you a timestamp which has not passed all over the world. So you can trust that the upper bound timestamp is definitely a timestamp in the future for everyone. With this, we can make sure that we can basically have exactly only one leader in our group and basically have serializability for our commits that we have. Now, how do we ensure this and keep this uncertainty, which we call epsilon in Throughtime, as low as possible? You can imagine if this epsilon, this interval is large, then our database is slow. If this interval is very small, our database can be fast. Because if you do a commit, you basically choose this commit timestamp in the future, and you wait out the time till this has passed, and then you do your commit. So if you have a large epsilon, you have to wait a long time to actually do your commit. So to minimize this epsilon, we installed a bunch of hardware in all our data centers. So we have a set of atomic clocks all over in our data center, and we have GPS time masters. So we have atomic time masters and GPS time masters. Now with the GPS time master, we can synchronize around the globe with a small epsilon, and then we use the atomic clocks to basically keep that drift low inside our data centers as well. And then if we request a timestamp, a true timestamp, we basically take a subgroup of these time masters. It can be GPS and atomic time masters. We look at all the true time timestamps that we have gotten back. And if there's any outlier, we just basically say we don't trust that time master anymore, and we kick it out. And then we basically take the majority and say, okay, this seems to be like a trustworthy true timestamp. Now, some of you might ask, say, like, okay, what happens if all my time masters, all GPS, atomic clocks fail in my data center? Is Spanner coming to a grinding halt and become unavailable? Actually, it doesn't. Because we can still go to another data center and get the true timestamp from another data center. But as mentioned before, like that increases the epsilon, increases basically the uncertainty interval because we have to travel to the other data center, we have to calculate all the round trip time into that and everything. So the epsilon will become bigger, but our database is still running. It's just running a bit slower. All right, switching gears a little bit and looking at it from the perspective of a query. So let's imagine I have a read query. So here in this case, select star from an event table where the name is JavaDay UA 2017. Now that request comes in from a client, and it's routed to a follower of my Paxos group. Now the follower, since this is a consistent, and in this case actually a strong consistent read, I want to make sure that I see the latest data. The follower basically goes to the leader of the Paxos group for the split and asks like, hey, do I have the latest data? It basically sends a timestamp and say like, hey, this is the timestamp of the data that I have. Is that the latest one? And if it is the latest one, the leader will just respond back, yeah, you have the latest data. And then the follower will serve that data. Now, in the case where the follower doesn't have the data, the leader will actually say, hey, you don't have the latest data, but just wait, it's already in flight. So it will not send the data with the response. It will just tell the follower to wait out the time till it sees the timestamp that is sent in this response. So the follower will wait out the time, and once it sees the timestamp of the latest data, it will respond back with the data. Now, there is something really powerful in Spanner, which we call time-bounded or stale consistent reads. Now, what is a stale consistent read and why is it powerful? The thing is, since we use this timestamp for global consistency, we basically can travel back in time in Spanner and give you a consistent view of the world. So like, there are no intermediate states where basically I took money from one account and it didn't credit it to another account. These states don't exist. Right? So, but with traveling back in time, there's something really powerful in the sense of that the followers or the replicas actually most of the time can serve the data without consulting the leader of the Paxos group. So here in this case, I'm sending a request and I say like, okay, I'm fine if the data is 15 seconds old. It's all right, you can serve me the data which is 15 seconds, up to 15 seconds old. And if the follower basically it checks like what's the latest timestamp of the data, it will check and see, okay, I have actually the data which qualifies for that statement and can serve the data right away. Now that might not seem very powerful in the sense of a regional instance, but imagine if you have a global replicated Spanner instance. Now in a global replicated case, you basically, for instance, have the read-write quorum in Europe, and then you have a read-only replica in the US and in Asia. Now, there might be clients coming in from Asia, and if they basically ask for some data where they say it's fine if it's 15 seconds old, you can get a response in a single low double-digit milliseconds for your queries, depending on the complexity of your query, of course. Now, if you do a strong, consistent read, the replica, the follower, has to first consult the read-write quorum, which I said would be in Europe. So you incur the physical round-trip time to Europe and back to make sure that you have served the latest data, which is then in the low 100 milliseconds to respond to the query. Now, how does the read-write transaction look like? So all our read-only transactions are lockless, so we don't need to acquire locks. We can just serve the data, which is pretty nice. Now, in a read-write context, we actually do need to require some locks. So let's just imagine I do a query. Now, it doesn't make sense to route this query for read-write transaction to the follower, because we know we need to involve the Paxos leader for that. So what we do basically is we route that traffic directly to the Paxos leader. So we have a lookup where the requests come in. We know basically where the leaders are, the majority. We choose a leader if multiple splits are involved. And then we send that directly to the leader. Now the leader, what it does is basically acquires some logs. It will respond with the query result. Then we do some modification. We send this modification to the leader, and the leader will send out the write requests to the commit for the followers. Now they basically, once we achieve majority, we say, okay, this has been persisted, and the leader can release the logs and respond with the data, and we're done. So these are basically the lives of the different kinds of transaction contexts that you have in Spanner, like from a read-only transaction with time bound, where you can basically travel back in time, and read-write transaction. Now, if it comes to the data model, you probably imagined already, since we support SQL, we actually have the traditional relational model, data model behind the scenes. So you have just tables as you're used to from relational databases, which have strongly typed columns. But we don't support things like referential constraints, foreign key constraints, for instance. We don't support things like UDFs, triggers, or stored procedures. Some of those are very poisonous in a distributed system. So they can basically bring a distributed system to a halt. Now we support one thing, which I would call foreign key constraint minus minus. And that is interleaving. Now, what is interleaving? Interleaving is basically that I interleave child data into a parent row. So imagine I had this example here of singers and their albums. So I had two tables, the singer table and the album table. Now, for my system, I usually, very often join these two tables. And if I join these two tables very often, it might make sense to actually interleave them. Why does it make sense? The thing is, with interleaving, we actually we take advantage of data locality, in the sense of that the data is co-located on the splits. So the table, the parent table rows, and the child table rows are co-located in the same split. Now this is powerful on the one hand, but it can be very dangerous on the other hand. So be careful if you use interleaving. For instance, if you interleave a large child table into a single row of your parent table, all this data ends up in one split. So you restrict yourself on the capacity of a split, so the boundaries, the storage boundaries of a split, and also all the traffic, all the queries and everything on this child table actually goes to the split. So you risk hotspotting. And that is also very poisonous against horizontal scalability. So be careful. It can be powerful, but you should be careful using it. Now, how does it look like when in SQL? We basically have a statement where we call interleave in, and that tells Spanner to interleave the child table into the parent table. Now, there's one constraint to it. You need to share the primary key. So in our singles table, our primary key was singer ID, and you need to lead with this primary key in your child table to be able to interleave. So what are a couple of schema don'ts if you move, for instance, from a MySQL or Postgres system? Now, before I go into this, one note. If you come from like a MySQL system or Postgres system or any other of the major database vendors in the relational database space, it's not going to be a lift and shift. I mentioned there are no stored procedures, triggers, or UDFs right now. So these are things that you have to consider. You might have to do some schema tweaking to actually enable the scalability that we can provide. Now, I mentioned a couple of schema don'ts here that are poisonous, again, in distributed systems or distributed database systems. Now, first and foremost is I got to love a feature in MySQL when I started using it, and that was an auto increment of an index key. So I had like an ID, and I just said like auto increment on index on insert, and then basically when I insert a row, it just gives you a new ID. Now, this is really poisonous in our system because all the data ends up in the same split. The same is true for things like increasing or decreasing primary keys, because that was one example. Another example for that is like timestamp. If you have a timestamp as a primary key and you insert a lot of data or you update a lot of data. So how would that look like? Here in this example, I have a user table, for instance, and I've chosen the last access time timestamp as the primary key. Now, every time I do this update, since we store and split our table lexicographically, it basically means that all that data, all these updates, go to the last split, and I'm hotspotting on that split. And by that, you restrict your scalability. So how can you avoid that? So one way to avoid this is using unique IDs version 4 or plus for your primary keys. Another thing is also using sharded counters. So how would the sharded counter example look like? You basically prefix your primary key with a sharding key, and by that, you enable that the traffic gets distributed across multiple splits, and by that enabling horizontal scalability. All right, switching gears and show a little bit like how you can get started with Cloud Spanner. Now, the first thing that I want to show, and the first thing that is you can start with basically, and let me pump this up a bit, is if you start with cloud.google.com/spanner. So we have a lot of information on there, and what I wanted to point out is at the end, like especially if you come from a MySQL system, we have some case studies of our early access program members that moved a sharded MySQL from their system to Spanner. So there's a quick Quizlet blog post which is very detailed and talks about all the challenges of migrating a system from a sharded MySQL to Cloud Spanner. So it's a very good read to see like the best practices for migrations if you plan them. Another thing that you see here is a blog post from Eric Brewer. Eric Brewer is the inventor or the author of the CAP theorem. And I'm going to talk a little bit more about the CAP theorem. But basically, this is an elaborate blog post and talking about like what's the relationship between the CAP theorem and Spanner. Now, if you want to create a database, this is the Google Cloud Platform console. And there are multiple ways to get to Spanner. The first one is you either can click on this hamburger symbol up here and then click find Spanner. You can search for it up here. And if you're a Vim user, you can just press / it automatically highlights into the search bar and type in Spanner. And then we click on it, and that is basically our entry point to create an instance. Now for creating an instance, I basically name it. So let's say JavaDay UA. It gives you an instance ID. And then I choose a configuration. So currently we have 4 regional configurations available. So I choose Europe West, and I say, OK, I want to have 3 nodes. Let's see if I have enough quota for that. Going to click Create. And once I've done that, within seconds, I basically have my instance at my disposal. Now I can go ahead and create a database. You can do this via the API. You can do this here in the console. I'm going to just show that here in the console really quick, can add columns. So let's say a name, string, and then I also add, for instance, age. Integer seems appropriate. I choose a primary key. In this case, I choose name as a primary key, and I click Create. Now again, in a couple of seconds, depending on the complexity of the schema, you have that available as well, and you can now start sending data to that database. Now, a very powerful feature of Spanner is online schema updates. Online schema updates allows you basically to evolve your schema while your database is running, while you're under load. So what I can do in my Syncos table, for instance, here, I can edit the schema. And I can edit the color and say, OK, I want to have the city where the singer is from. I can say done, I can stay safe. And again, you can do that with APIs as well. And then it actually packs this online schema, this schema update into a transaction. And once this transaction committed, it is available to your applications. All right. Another thing that I want to show really quick is queries. So I have an example schema, and I want to show you this example schema. So I built the keynote demo for our annual event to showcase Spanner. And for this keynote demo, I was looking for a somewhat realistic scenario, what would be out there where we need global consistency, where we need a system which scales horizontally, but also has like all the features of asset transactions and global consistency. Now I came up with a scenario where you have a ticket broker system. So you have a ticket broker which works all over the world, and you have basically, think of Ticketmaster or something like that, where you have a lot of event organizers that put in events, and then you have people that want to buy tickets. Now, as you can see here, this is like roughly a schema that you could imagine to have. You have like events, you have multi-events. If multi-events are basically like tours, for instance, you have a Bruce Springsteen tour or Coldplay tour that has like multiple events. And then you have things like, okay, this event has to happen in a venue. This venue might have different seating categories, like assume like general admission, premium, VIP seating. And then based on the event, this has different prices for these seating categories. So you see, like it gets, like if you think about it a little bit, it gets more and more complex pretty quickly. Now, as you can see, I also used, in this case, interleaving for one special case. So if I ask for venues, most of the time I join this with the seating categories that are available in my venues. So I made use of interleaving here to have that data co-located. And then you see a bunch of other tables where I keep like global counters for how many tickets I sold and things like that. Now, there's one thing that I want to point out in this query here that you see. So this query basically asks for tickets that are available from the 5th of November, so today, till the 11th of November. And it asks for all the events that are available in Ukraine. Now, there's one thing that you don't see here. You don't see any added complexity of sharding. This is just a normal SQL query, how you would imagine it to be from a traditional relational database system. So all the distribution behind the scenes, the query execution, the distributed query execution, things like that, is all handled for you. So if we run this query really quick, you're going to see here that we have 2 events and then a couple of tickets still available. Now, I don't want to like end with like only showing you the console, how you actually interact with Spanner in the console. So I have a little demo as well for showing you, if I find it, how to actually get started in Java with Cloud Spanner. So everything starts with a POM, of course. Any Gradle users here in the room? Everyone with Gradle? Okay. Maven? Okay, still the majority. All right, so in this case, I'm actually using Maven. So what you need actually is you need the Cloud Spanner client library, and then we have 2 more packages that I'm choosing here is Guava and the Google Auth client library to actually simplify more auth flow for authenticating against my database. So very straightforward. Now, if I want to get started with my database, here in this case, I want to do a read-only transaction. The first thing is I need to authenticate against Cloud Spanner. Now, with Google Cloud Platform, this is actually pretty nice and easy in the sense of if you have our gcloud SDK installed or you have that running on one of our GCE instance, you have something called the default application context. And you can actually make use of that to authenticate against your database. Now, you, of course, can also create a service account and use a service account to authenticate. But here in this developer case, I just make use of this. All right, the next thing is I need like a connection. Now, so basically get a spanner options object using a builder. I name my instance, I name my database ID, and the project ID I get from my authentication context. And then I use all this, as you can see here, to create my database client. Now, the next thing is I want to have a read-only transaction. So I go to my database client and I get a database single-use read-only transaction. And then, of course, I want to have a query that I'm running. So basically, I use this transaction context that I have, and I can use SQL, or I can use the read APIs. I create a SQL query with some parameter placeholders that I'm binding down here, and I'm just, at the end, running it. So let's see. Yep. Right. So basically here, since I run it already, I'm just looping through my result set. Now you can point in your result set to the columns in different ways, either by a positional argument or by name. In this case, I use the positional argument. And then last but not least, I'm just running this, and I have a problem. So let's see, what did I do wrong? Of course. It's good. Let's see if this works. Live debugging, fun. All right, that looks a little bit better. All right, so this is a read-only transaction, pretty straightforward. Now, I want to switch gears really quick to a write-only transaction. Now, I showed you already the step. Now, in a write-only transaction, there's some special case to it. I actually need to work with mutations. So here in this case, I have a write-only transaction that I have, so I can basically just say db client write and then write mutations. Now, there's a special thing about mutations. In Spanner, mutation is not by row, it is actually by cell. So when you write a row in Spanner and you have a table with 5 columns, this is 5 mutations. If you have an index on this table, which indices another 2 columns of your table, you actually have an additional 2 mutations per row that you insert. So you have 7 mutations. Why is this important? There's a transaction limit of 20,000 mutations per transaction in Spanner. So if you ever see this arrow and you think like, I'm just inserting like 1,000 rows. Why am I, or changing 1,000 rows? Why am I getting this 20,000 limit? The reason for that is basically that you modify more than 20,000 cells. Now let's run this really quick. It basically just inserts an account into my database, and you see here it was written. So now the next thing that I'm going to do, I want to actually do some changes to this. So there's one more thing that we do about changes. The client library actually supports rerunning of transactions. So we basically have here this transaction callable that we create. And in this transaction callable, we have a run function that we override. In this run function, we basically get a transaction context where we do the read, and then we do the modifications. We write these modifications to a buffer, and then basically give this whole thing to the client, and the client runs this for you. Now, if there's any transaction failure, then the client can basically rerun that transaction and make sure it gets committed. And if you run this again, I can go back to my database and can see my demo database and go to the account table. Then you see here the data that I have an account. Yeah, that was actually the one. All right, so last but not least, I want to briefly touch on the cap theorem. So some of the people asked, like, does Spanner defeat the cap theorem? So now what is the cap theorem? The cap theorem basically describes 3 qualities in a distributed system, like the qualities between that you have to choose for distributed systems. These 3 qualities are C, stands for consistency, A stands for availability, and P stands for partition tolerance. Now, what does it basically mean? like just imagine if you have a CA system. A CA system basically means it's always consistent and always available, even in the case of partitions. Now, please, who knows a CA system? Anyone? Anyone? Yes, you know a CA system? What's a CA system? It's a relational database, yes. Oh, but in what case? It's a special case. Exactly. A single system, a single host system database is a CA system. But there are no distributed databases out there that are CA. If you see a distributed database that claims to be CA, get really suspicious. There are none out there. So now then you have the two other arcs that you can choose between. You can either be a database system which is always available, even in the case of partitioning, but then you're not consistent. So you have databases out there that support this model, but basically the partitions can drift away, right? And you have to reconcile this drift. And you have other databases which decide not to do this and say, okay, they are CP systems where they are consistent in the case of partitioning. And that basically means that they become unavailable. Now, Spanner is a CP system. It becomes unavailable in the case of partition. But why does Google actually provide a 4 nines for regional and 5 nines for multi-regional SLA? The thing is that this case is really, really unlikely if you have really, really good architecture and infrastructure. Now we have redundancy in our network, we have redundancy of like how the database is distributed, and that's the possibility where we can say, with the quality of hardware and infrastructure that we have, we can provide a system which becomes close to a CA system, but is not. It is a CP system, and we are not defeating the CAP theorem here. With this, I thank you very much for your attention. And if you have any questions, please come up forward or take the mic. I know that I run already a little bit over time. I appreciate that you all stayed, even though the lunch is probably already been served. So if you have any questions, I'm happy to take a couple. You also can come up after the talk, and I'm happy to answer them. Or reach out to me @hosteriosity on Twitter. Thank you very much.